Hey guys, and welcome back to another video on the channel. In today's video I'm going to be proving all of calculus from pretty much start from the first derivative all the way up to the volume of revolution. So all we're going to do is just imagine an xy axis, and what we want to do is work out how we can work out instantaneous gradient. So we know what gradient is. Gradient is rise on run. So how much we change in the y direction compared to how much we change in the x direction. The rise representing how much we change vertically and how much we change horizontally, and thus giving us this slope called a steepness. Okay? So we've calculated this stuff for simple lines. So for example, if we have a line like this, we can calculate the gradient by measuring this change in x compared to this change in y. And that's what we call gradient. Gradient is change in y over a change in x. However, when we have a curve like this, the steepness changes all the time. And we don't really know how to find that to start off with. So what we're going to do is just picture a function. So all I'm going to do is make this probably a little bit smaller, or move this over here just so I have a bit more room. So a function is like this. Any function could be a quadratic, a logarithm, or anything like that. The point is, a function is an equation that depends on x purely, and one x value gives you one y value. Okay? So let's say we want to work out an instantaneous gradient. So let's just move the curve a bit down slightly so I have a bit more of a point I want to look at. So let's say I want to find the instantaneous gradient there. Righto. So all we're going to do is look at our point there. So let's just say, alright, that point is x, and I go some distance h in this direction to x plus h. So whatever this x coordinate is, I've moved that distance h to the right to this one here. Righto. So now I've got 2 points on my curve. So if I put an x into my function, I'll get f of x, which is over here. So this would be f of x. And if I put an x plus h, I'll get f of x plus h. So now I can actually work out a gradient here because I have a change in x and a change in y. Okay? So my rise over run will be the following. So how much I've risen, I've gone from f of x to f of x plus h. So that will be the difference of f of x plus h minus f of x. So that will be the length of this triangle here, that bit there. Okay? The length of this side bit here will be the difference between x plus h and x. So it'll be x plus h minus x. Okay? And we can see straight away the x's cancel out. So if we take a look at this expression here again, we have f of x plus h minus f of x. Okay? The x's cancel out, and all we're left with is h. Now this is the expression for my slope between 2 points. Now this would be an average if I had just 2 points, but I want an instantaneous gradient. I basically want the steepness at 1 point. Now the way I can make this 1 point is I can make this distance as small as possible. In other words, I'm going to move this point on top of this point here and get an instantaneous steepness. So in order to do that, we need this distance to be as small as possible. So what we're going to do is apply this thing called a limit. We're going to let h go to 0. And if we do that, we'll get an expression for our instantaneous gradient. Okay? So all we're going to do is apply a limit. And now the way we'd write this is we write lim, and what we're applying the limit to. So h is going to go to 0 of this expression here. F of x plus h minus f of x divided by h. And this is the expression of the derivative. This is what we call f dash. So f dash represents our gradient function. So a line doesn't really have a function associated with its steepness because the steepness here is the same as the steepness here. However, with a parabola, the steepness here is different to the steepness here. This region here is a lot steeper. So if we applied this, we could find a function to measure the steepness of any function, pretty much. So for example, if we wanted to find the steepness for a parabola, let's say so that's a terrible looking parabola. So let's say we had the parabola just y equals x squared. we can find the steepness at the point x equals, let's say, 1 here, okay? So all we will do is place this into our equation. So f of x is x squared, and f of x plus h would be x plus h all squared, okay? I'm going to expand this. This is x plus h times by x plus h. So if I multiply x by x, I'll get x squared. If I multiply x by h, I'm going to get x times h. Same thing here. And then, oh, sorry, that's going to be a h. And then finally, h times h is going to be h squared. So I'll get x squared plus 2xh plus h squared. Okay? So if I plug this in here, this is what I'm going to get. I'll get f dash of x is going to be equal to f, the limit, as h goes to 0, of my f of x plus h, which is this expression here. So I'm just going to move it to the left really quickly. So this minus f of x, so this guy here, divided by h. Okay? Now we can see the x squares cancel out, and all we're left with is f dash of x is equal to the limit, as h goes to 0, of 2xh plus h squared on h. Now I can't apply this limit straight away, because if I put in h equals 0, I'll have a 0 divided by 0. So what I can do to get around this is actually factor out that h in the numerator and the denominator. So in other words, I can take out a h at the top there, and it'll leave me with that expression. And then I can cancel those h's, so all I'm left with is this expression for the derivative of x squared. We get 2x plus h. Now I'm going to apply the limit to this equation here. As h goes to 0, this goes to nothing, so f dash of x is 2x. So this equation gives me the steepness at any point on the parabola. Now the steepness is going to change depending on the x value. So we got f dash of x to be 2x. So if I want the steepness at x equals 1, I put in 1. And the steepness is going to be 2. If I want the steepness at this point, let's say x equals 2, I can see this point's going to be steeper, so I'm expecting a larger number. So I'll go f dash of 2. Gives me 2 times 2, which is 4, which makes sense. So whatever number you put into f dash gives you the steepness at that instantaneous point on our curve. Now that's all well and good, but we don't want to be plugging everything into this equation here every single time, especially if it's like x to the power of 6, because then you'd have to work out this by hand, and that would take a very long time. So what we're going to do is a little shortcut. So this is what we call the first principle. So f dash of x is this, and we can see that from our diagram, which we proved above. Now we want to start finding some shortcuts to find the derivative of functions very easily, rather than just constantly plugging into here. So what we're going to do is just pick the most generic case. F of x is equal to x to the power of n, and n is any number that isn't 0. Okay? So all we're going to do is plug this f of x into our first principles and see what we get. So f of x plus h will be then x plus h all to the power of n. Now we're going to expand this using the binomial theorem. So if we expand this using the binomial theorem, we're going to get x to the n plus n choose 1 multiplied by x to the power of n minus 1 times by h plus n choose 2 x to the power of n minus 2 h squared, and that goes on forever, and we just keep increasing those powers until eventually we get to plus h squared. So that's the generic expression for expanding a polynomial. Okay? So what I just did there was use the binomial theorem. Righto, so now all I'm going to do is plug this into here and this into here. So this is what I'm going to get. F dash of x is equal to the limit as h goes to 0 of this entire thing here. Now, we're going to work out what this is very quickly. So n choose 1 means n choose 1. And the way we calculate that, if we write it down here, so n choose 1 means n factorial over 1 factorial times n minus 1 or factorial. Okay? Now let's work out what factorial means. So, factorial means to multiply from that starting position downwards till 1. So for example, 5 factorial means 5 times 4 times 3 times 2 times 1. Okay? 10 factorial means 10 times 9 times 8, and you get the picture, all the way down to 1 pretty much. Okay? So, n factorial means n times the number after n times the number after that number, so on and so forth. Now this bit here is just n minus 1 factorial. So if I put that in here, I'll get this. So if I just move this stuff to the side, n choose 1 is going to be n times by n minus 1 factorial on 1 factorial times n minus 1 factorial. And we can see those two cancel out. Now 1 factorial is just 1, so all we're left with is n. So this coefficient here is just n. So when we plug that into our equation up here, we're going to get x to the n plus nx minus 1 times by h plus the rest of this nonsense here pretty much. So all that pretty much with all the h's. Minus x to the n, which is our f of x on h. Okay? Now I'm going to get rid of all this really quickly. Right. So we can see that will cancel out with that. Now all these terms here are from our binomial theorem, but they all contain h's. Okay? So what I can do is actually factor out a h out of all of them. So I'll get f dash of x. It's going to be the limit as h goes to 0. And I can factor out a h out of all of them. This will just be n times by x n minus 1 plus n choose 2 of x to the n minus 2. And this will be h now, plus so on and so forth. And the final term will be h n minus 1. All on h, and that h can cancel out, so we won't have a divide by 0 anymore. Righto, so now we have this expression. Now every single term past here is going to contain a h in it. So if I apply the limit, all of those turn to 0, and the only thing that's left is this. So in other words, we get f dash of x is equal to n times by x to the power of n minus 1, when f of x is x to the n. Righto. So, if we want to differentiate a polynomial, we just got to bring that power down the front and subtract the power by 1. Which, if we look back at this first one up here, is what we did. So we said f dash of x was 2x. All we did was bring that 2 down the front and subtract the power by 1. Righto. So now we're going to start introducing some notation. So, we're going to introduce this. Now this is going to mean differentiate with respect to x. Okay? So it's going to be called the differential operator. So the operation of the derivative. And this x down here is going to be telling me what variable with respect to. So for example, if I'm differentiating with respect to x of 5y, nothing gets affected there really because there's no x's. It's telling me what variable I'm differentiating with respect to. So now that we've introduced that notation, we can now write this simple rule called the power rule. Okay? So if I want to differentiate with respect to x to the power of n, that is equivalent to bring that power down the front and subtracting the original power by 1. So this is what we call the power rule. Okay? Now that's how you differentiate a polynomial. However, that doesn't show every single function. Because remember, that's only for a polynomial. But what about Euler functions, sine curves and stuff like that? we still need the first principle. So, using what we've established from our diagram, we're going to prove a couple other things. So, this is the definition of the derivative. The instantaneous steepness of a slope. Now, what if the slope is in the power of x? So, for example, let's look at another function in particular. Let's look at sine x. So, for example, f of x equals sine x. What is f dash of x going to be? Okay. So all we're going to do is plug this into our definition and see what we get pretty much. Okay. So if f of x is sine x, that means f of x plus h is going to be sine of x plus h. Okay. So that means f dash of x is going to be the limit as h goes to 0 of this guy here, so sine of x plus h minus sine of x on h. Okay. Now this isn't very helpful at the moment because we can't really break that up because of these terms here aren't like terms. But what we can do is break up this guy using a trig identity. So the sine of two sums, so a plus b, is equivalent to sine of the first one multiplied by cos of the second one plus sine of the second one multiplied by cos of the first one. Okay? So using this trig identity, we can break up this expression here. So we can go, alright, sine of x plus h means sine of x cos of h plus sine of h cos of x. Right. Now that would be a lot easier to put into here, and then we can start breaking stuff up. Okay. So what we're going to do is rewrite that. So f dash of x is equal to the limit as h goes to 0 of this guy here, so sine x times cos of h plus sine of h cos of x minus sine of x all over h. Righto. Now, the only thing I can see in common in the top bit is these sines of x's. So what I'm going to do is move them closer together. So in other words, I'll get f dash of x is equal to the limit as h goes to 0 of sine of x times cos of h minus sine of x plus sine of h cos of x all on h. Okay. Now here I can factor out a sine of x out of this expression here. So what I'm going to get on the top there is, well, sine x multiplied by this. So sine x, take that out, I'll just have cos of h minus sine x, and I factor out the sine x, I'm going to get minus 1. Okay? Plus sine of h cos of x all on h. Okay. Now, as h goes to 0, this turns into cos of 0. Now, cos of 0 is 1. So here, I'm going to get 1 minus 1, which turns this whole guy into 0. So in other words, I can just rewrite this like this. The limit as h goes to 0, and that term is 0, so all I'm left with is sine of h times cos of x divided by h. Now, I can remove my cos of x because there's no h's, so the limit doesn't apply to this because it doesn't have any h's, so the x variable is independent of our limit. So if I wanted to, I could just take the cos x outside the limit. So if I just take them out, and I make this a bit closer, let's see how this goes. So I just take them outside of the limit. So I get f dash of x is cos x times this limit. Now this is a famous trigonometric limit. If you have the limit as theta goes to 0 of sine of theta on theta, that is equivalent to 1. And that is the exact same limit we have here. So I can replace that whole thing with just 1. So that means f dash of x is cos of x when f of x is sine of x. So what that means in terms of our new notation now is if I differentiate sine x, I'm going to get cos of x. Now, will it be the same if I differentiate cos of x? Will I get sine of x? We can't be fully sure at the moment, but we can find out using the same thing. So, if f of x is cos x, what will f dash of x be in this case here? Okay. So what we're going to do is use our derivative again, the first principles. So the limit h goes to 0 of f of x plus h minus f of x all on h. Okay. So f of x plus h is going to be cos of x plus h. Now we're going to break this apart straight away rather than waste our time, because if we just plugged it in straight away, we get a similar situation to this where we can't really break it up. So all we're going to use is a trig identity again. So if I move this guy to the side, cos of cos of a plus b is equal to cos of a multiplied by cos of b plus, actually no, it's not plus, it's minus, sorry, minus sine of a multiplied by sine of b. Okay, so that means cos of x plus h is equal to cos of x times by cos of h minus sine of x multiplied by sine of h. Okay, so if I plug this into our derivative now, I'll get f dash of x is equal to the limit as h goes to 0 of f of x plus h, which is this guy here, so cos of x cos of h minus sine of x sine of h minus cos of x. Okay. Now we're going to do a similar thing to the sine term. We're going to group our coses because that's the only thing in common in this top bit here. So f dash of x is going to be the limit as h goes to 0 of cos of x cos of h minus cos of x minus sine of x times by sine of h, all on h. Now I can factor out a cos of x in this expression here. So I get f dash of x equal to the limit as h goes to 0 of cos of x factored out of this, so I'll have cos of h minus 1 minus sine of x times sine of h on h. Okay. As h goes to 0, this will turn into cos of 0, which is 1. So effectively I'll have 1 minus 1, which is 0, so that whole thing there disappears. So what I get is f dash of x is equal to the limit as h goes to 0 of minus sine of x sine of h all on h. I can take out minus sine of x out of the limit because it's independent because of the variable. The x doesn't depend on h at all, so I'll get f dash of x is equal to minus sine of x, the limit as h goes to 0 of sine of h divided by h, and we know, of course, this guy here is 1, so that means f dash of x is minus sine of x when f of x equals cos of x. So what that means is the derivative of cos of x is equal to minus sine of x. Okay, so it wasn't exactly sine, but pretty close to it, I reckon. Okay, righto. So we've proved power functions and two trig functions. Okay. Now we won't be able to prove the tan function just yet because there's a couple other things we need to prove beforehand. What we can do is start taking a look at a special curve, Euler's one. So if we take a look at f of x equals e to the power of x, what is f dash of x going to be? Okay? And you guessed it, we're going to use the first principles again. So f dash of x is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. Okay? So if f of x is e to the x, that means f of x plus h is going to be e to the x plus h. So f dash of x, the limit as h goes to 0 of e to the power of x plus h minus e to the power of x all on h. Now, there's something we can do before we factor anything out. We can change how this looks. So if we recall our index laws, if we have a to the n times by a to the m, so if we have two numbers that are the same base, we can add their powers together if they're being multiplied. But we can do the reverse. If we have this expression, we can rewrite it like this. So in other words, e to the x plus h is the same as e to the x times by e to the h. So we're just doing the reverse pretty much, which is what we're going to do in pretty much our expression up there. So I'll just move this to the side, and I move this out of the way. So I can get f dash of x equal to the limit as h goes to 0 of, and then I can break this up, e to the x times by e to the h minus e to the x all on h. Now I can see there's something in common, this guy and this guy. So I can factor them out. So I get f dash of x is equal to the limit as h goes to 0 of e to the x on e to the h minus 1 all on h. Okay? I can take e to the x out of the limit now because it's independent of h. So f dash of x is going to be e to the x, the limit as h goes to 0 of e to the h minus 1 all on h. Now we're probably thinking, how do I know what this is going to be? Well, let's work out where e is defined. So this specific limit here is what we have. This equals 1 when a is equal to e. That's where it's defined. This is the exact same limit we have here, except a is e. So if a is e in that case, that means this entire thing here must be equal to 1. So in other words, it's e to the x times by 1. So that means f dash of x is equal to e to the x, when f of x is e to the x. So that means when I differentiate e to the x, I get e to the x. It doesn't change at all. Okay? And that's how you differentiate that term. Righto. So we've done powers, cos and sine, and Euler's function. Now we need to do logs. Now specifically natural log. Okay? So if we have y equals natural log of x, we write it like this. But ln of x just means log base e of x. Okay? So why don't we just write it like that? So we get y equals log base e of x. And now we're going to change how this looks. So if you recall, if we have a to the q equals b, we can write that as a logarithm. This can be rearranged as log base a of b is equal to q. So in other words, we've got this expression here. We want to turn it into an exponential. And the way we're going to do that is, alright, that's just e to the power of y equals x. Pretty simple. Now, we're going to differentiate both sides. So if we differentiate both sides, not with respect to x, but with respect to y, this is what I'm going to get. I'll have d dy, e to the y, and differentiating this side we just realized is going to be e to the y. Now, because this isn't y, we can just write that as dx dy. We can just move the x up there. So we get dx on dy. So dy dx is going to be 1 over e to the x. Now dy dx is another way for writing f dash of x. Okay? Now we just worked out what e to the y was. It's x. So that means dy dx is 1 over x. So what that means is if you differentiate natural log base e, you're going to get 1 on x. Okay? And that's it for that one. Righto. So we've done sines, cos, powers, Eulers, and logs. Now we're going to take a look at inverse trig, specifically inverse sine. So if we have y equals sine inverse, now we're going to include a number in there as well. Let's say we have x on some number a. How do I know what dy dx could be? Okay? Well, we don't, but we do know how to differentiate sine. So why don't I just try and make this into a sine? So what if I sine both sides? So I'll get sine of y equal to x on a. And if I move that a up there, so let's say a is a number for this case here. If I move the a up there, I'm going to get x equals a sine of y. Now I can differentiate both sides, but it'll be with respect to y now. So in other words, I'll get dx dy. If I differentiate sine, I know what that is now. That's going to be cos. So I'll have a cos of y. Now I can work out dy dx is. I can flip the whole thing. So dy on x is going to be 1 on a cos of y. Now, I don't want to write dy dx in terms of another variable y. I want to write it just in terms of x. So we've got to work out what cos of y is. So a great way to use this is using Pythagorean's identity. So sine squared of an angle plus cos squared of an angle is equal to 1. So that means sine squared of y plus cos squared of y is equal to 1. Now we want to get cos of y by itself. So I move the sine squared y onto the other side. So I get cos squared of y equal to 1 minus sine squared of y. Then I'm going to square root both sides. So I get this. And now I know what cos of y is. So I can place this guy straight into here. So I'll get 1 on a square root of 1 minus sine squared of y. Now, I know what sine of y is. Sine of y is this guy here. So I can place this guy down here. So I'll get dy dx is equal to 1 on a times the square root of 1 minus, now, sine squared of y just means sine of y, or squared. It's just a notation for it. But I know sine of y is x on a. So that means sine squared of y is going to be x on a all squared. Applying that index law, I'll get x squared on a squared. So I can put that straight in here. So minus x squared on a squared. Okay. Now I'm going to change how this looks a little bit. So I'll have, what I have is dy dx equal to 1 on a square root 1 minus x squared on a squared. I'm going to factor out an a squared out of here. 1 over a squared to be specific in this square root. So what I'm going to have is this. 1 over a squared, factored out, 1 will be turned to a squared, because if I were to multiply that back out, that front bit will turn into 1, and this bit's just going to be minus x squared. Now, I can separate this. I can rewrite it as a product of 2/3 times the square root of 1 on a squared times by the square root of a squared minus x squared. This 1 on a squared square rooted is just going to be 1 on a. 1 on a times by a is just 1. So that front bit is just going to be times by 1, and we get dy dx is the square root, is specifically 1 over the square root of a squared minus x squared, where a is the number under the x in the sine inverse. So in other words, if you have sine inverse of x on a, and you differentiate that, you're going to get 1 over the square root of a squared minus x squared. Okay? Now we're going to do the same thing for cos inverse. So, let's say we have y equals cos inverse of x on a. We don't know how to differentiate cos inverse because that's what we're trying to do. So we do know how to differentiate cos, so this is turning into a cos. So cos both sides, and that gets rid of that cos inverse. So you get this following expression. Now we're going to differentiate both sides with respect to y. Once we move that a up there, so we get x is equal to a cos of y by multiplying both sides by a. So dx dy. I know how to differentiate cos now. It's going to be minus sine, so it'll be minus a sine of y. So that means dy dx is going to be negative 1 over a sine of y. Now I've got to work out sine of y is again. So I've got to use Pythagorean's identity again. So sine squared of y is going to be 1 minus cos squared of y. Square root both sides, so I get sine of y equals the square root of 1 minus cos squared of y. I know cos squared of y is just going to be cos of y all squared. Cos of y I know is x on a. So that means this is going to be x squared on a squared. Okay? So I can replace all of this there. So I get, alright, sine of y is equal to the square root of 1 minus x squared on a squared. And then I can replace this bit with all of this. So I'll get dy dx equal to negative 1 on a times by the square root of 1 minus x squared on a squared. And then we can start factorizing this again. So dy dx is equal to minus 1 a, and then I'm going to take out a factor of 1 on a squared. So 1 on a squared, I'll get a squared minus x squared. Okay? Then I can split that up into surds. So I'll get a times the square root of 1 on a squared times the square root of a squared minus x squared. This front bit's going to turn into 1 over a times by a, and that's just 1. So dy dx, in this case here, is going to be minus 1 over the square root of a squared minus x squared. So it's very similar to sine, except instead of a positive, it's going to be a negative. So if you differentiate cos inverse of x on a, you're going to get minus 1 on the square root of a squared minus x squared. Okay? Right, I'm going to have a little drink for a second. This is a long video. I ain't going to edit this. Right. So, we've proved in all those. Those are some important functions. Now, we can't really prove anything else without some other stuff. So, let's say we had a function. Let's say we had y and we had f of g of x. So in other words, a function inside another function. So in other words, let's say we had sine of x squared. How do I differentiate something like that? Well, what we can do is make a substitution. Let's call g of x u. So let u equal g of x. So that means y is going to be f of u, a function of u. Now, if I go, alright, if I differentiate this with respect to x, I'm going to get du dx, and here will be g dash of x. Here, if I differentiate this, I'll get dy du, gives me f dash of u. Now, if I multiply these things together, something incredible happens. So if I get du dx, and I times that by dy du, the du's cancel out and you get dy dx, which is insane. So in other words, dy dx is going to be g dash of x times by f dash of u. Now, what was u again? U was g of x. So I can place that back in there. So if y equals f of g of x, that means dy dx is going to be equal to g dash of x multiplied by f dash of g of x. So what the heck does that mean? So what does this mean? It means if you want to differentiate a function inside a function, you differentiate the inside and you multiply by the differential of the outside. So for example, if we have sine of x squared now, my inside function, my g of x, is x squared. And my f is going to be sine. So that means f dash is going to be cos of x squared, because we leave the inside function, and g dash of x is going to be 2x. Multiply these two together and you get the derivative. So the derivative of sine of x squared is 2x cos of x squared. So now I know how to do that. So if you have a function next to a function, you differentiate the inside and you multiply by the differential of the outside. And that is what we call the chain rule. So chain rule. And this rule is very important because it's going to help us prove a couple of things. So if we have, let's say, y is equal to f of x to the power of n, dy dx is going to be f dash of x times by n brackets f of x to the power of n minus 1. Okay? So it's chain rule there. Inside, function differentiated, multiplied by the differential of the outside, which we can see is the power rule, which we just proved. If I have y equals sine of f of x, dy dx, differentiate the inside, so f dash of x, times by cos of f of x. If I have y equals cos of f of x, dy dx will now be f dash of x times by minus sine of f of x. Okay? If I have y equals e to the f of x, dy dx is going to be f dash of x times by e to the f of x, because e doesn't change. The Euler expression stays the same, stays constant forever. Okay? Now, if I have y equals ln of f of x, dy dx, differentiate the inside one, so f dash of x, multiply differential of the outside, so 1 over f of x. So you get f dash of x divided by f of x. If we have a sine inverse, so if we have y equals sine inverse of f of x, differentiate that inside, so we get so dy dx is equal to f dash of x times by 1 over square root of 1 minus f of x, all squared in there. Okay? Now, in this case here, we had pretty much a very simple scenario. So in this case, we had, if you imagine, we have this scenario here, f of x on a. But let's say a was 1 in this case here. So that would be squared, and the f of x would just go there. Very similar to our rule which we just proved up here, except we just let a equal 1 in this case, because we're accounting for that whole thing as a function. So if we put the whole function there, it accounts for it pretty much. Okay? So, and then the same thing with cos inverse. If we have y equals cos inverse of f of x, this implies dy dx is equal to f dash of x times by negative 1 on the square root of 1 minus f of x all squared. Okay? And that's it really. That is the chain rule applied. Now, a function inside a function isn't the only scenario that appears in maths. Most of the time we get a product. So in other words, what do we do if we have y equals f of x times by g of x? How do we differentiate that? Well, when all goes to failure, what we're going to use is the first principles. So the first principles is the limit as h goes to 0 of f of x plus h minus f of x divided by h. Now, this f of x isn't this one here. It's talking about the entire thing, okay? So, my f of x plus h, so let's just write this as a different function in this case. Let's use like h. Not h, I'm sorry. Let's use like, I'm just trying to think of a letter, q. Okay, so q is another function of x, okay? So that means q of x plus h. So q of x is f of x times by g of x. So that means q of x plus h is going to be f of x plus h times by g of x plus h. Okay? So we can plug this guy in here, and we can plug this guy in here. So what we're going to get is this. The limit, so this is dy dx. Dy dx is equal to the limit as h goes to 0 of f of x plus h times by g of x plus h minus f of x times g of x, all on h. Now, we can't do anything at the moment because it's kind of broken. We can't release it, can't find anything in common to do stuff. So, what we're going to do is add in a specific term. We're going to add in pretty much this guy multiplied by this guy. So something in common in both of them. Now you could have chosen the other ones, it doesn't really matter, it'll work out the same. So what I'm going to do is technically add nothing. I'm going to plus f of x plus h times g of x, and I'm also going to subtract that. So I'm technically adding nothing. I am plussing 1 and minusing 1. Same thing. Okay? So if I put that in the middle of our limit, this is what I get. Dy dx is equal to, let's move this guy down because we're running out of room, to the limit as h goes to 0 of f of x plus h times by g of x plus h, and then we're going to insert this little cheat here. Now I'm going to rub that out because that's annoying me. Plus f of x plus h multiplied by g of x minus f of x plus h times by g of x minus the last term, which is f of x times g of x. All over h. Rightio. What are we going to do now? Well, the reason why I put that in is because with this front bit, I can factor out something. I can factor out an f dash of x plus h. And this back bit here, I can factor out a g of x, which is what I wanted to do. So I get dy dx is equal to the limit as h goes to 0, and then I'm going to factor this out at the top. So I get f of x plus h times by g of x plus h plus g of x. Okay. Oh, whoops, sorry, I wanted that the other way. All I'm going to do is group these other terms. So rather than the plus be there, there we go, is my rubber working now? Sorry guys. Oh. So all I'm going to do is just switch the positions of these guys because I just wrote it out wrong. So what I want to do is write like this. So dy dx equals the limit as h goes to 0 of, and then I'm going to have f of x plus h times by g of x plus h minus f of x plus h times g of x plus f of x plus h times g of x minus f of x times g of x. So that bit there. So f of x times g of x. All on h. Now, I can factor out what I wanted to now. So in this guy here, I can factor out my f of x plus h, and in this guy here, I can factor out g of x. So dy dx is equal to the limit as h goes to 0. Then I can factor that out. So I'll get f of x plus h, brackets g of x plus h minus g of x, plus factor out g of x of f of x plus h minus f of x on h, brackets of everything. Righto. Now I can cut them in two like I've just done there. So just imagine I've split it up into two separate fractions like I have here. And what I can see is I'm going to apply the limit to every single expression I have. So in other words, I get dy dx equal the limit as h goes to 0 of f of x plus h multiplied by the limit as h goes to 0 of g of x plus h minus g of x on h plus the limit as h goes to 0 on g of x multiplied by the limit as h goes to 0 of f of x plus h minus f of x on h. Righto. So as h goes to 0, this turns into f of x, because f of x plus h, if there's no h there, it's just f of x. So you get dy dx equals f of x. This, if you hadn't recognized it, is the first principle, so that's just g dash of x, so f of x multiplied by g dash of x. This doesn't have a h, so I can just write that as plus g of x. And then finally, this last bit down here is also f dash of x. So I can just write that as g of x times f dash of x. Righto. And this is what we call the product rule. Product rule. So if you have y equals f of x times by g of x, dy dx means differentiate the first one or the second one first, and then plus the sum of the one you didn't do. So example, leave f of x, differentiate g of x, plus leave g of x, and differentiate f dash of x. F of x, sorry. And that's it. Righto. That's what we call the product rule. Now, let's take a look at one last scenario. So we've dealt with this scenario where we have a function inside another function. We've had this scenario where we have the product of two functions. But what about the quotient? So in other words, f of x divided by g of x, or q of x. We're going to tackle this one. So this is what we call the quotient rule. So, quotient rule is very similar to the product rule. Quotient rule, we have y equals f of x on g of x. We can just rewrite this using index law. So for example, 1 on g of x is the same as g of x to the power of negative 1. Is it not? So let's just write it like that. So we get y equals f of x times by g of x to the power of minus 1. And what we can see now, we have a product rule. So if I differentiate it, I differentiate the first term and leave the second one. So I get dy dx equals f dash of x times by, and just leave this guy here, plus leave f of x, and then differentiate this guy here, which is going to be a chain rule with a power rule in it. So bring the negative 1 down the front, so times by negative 1 g of x, and subtract the power by 1. And then we have to bring out the derivative of this, so times by g dash of x as well, because it's a chain rule. Righto. Let's try and rearrange this and simplify this. So dy dx is going to be f dash of x on g of x plus negative f of x times by g dash of x on g of x all squared. Now we can combine these two together once they have common denominators. So what I can do is a little trick. I can times this first bit here by 1 by technically timesing both in top and bottom by g of x. So if I do that, they would cancel out to give 1. But it's going to change this to have the same denominator as that. So I get dy dx equals f dash of x times g of x on g of x all squared plus minus f of x g dash of x on g of x all squared. I can combine them together because they have the same denominator, so I get dy dx equals f dash of x g of x minus f of x g dash of x all on g of x all squared. Okay, and this is if we have y equals f of x on g of x. So this is what we call the quotient rule for differentiation. Okay, righto. Now we've done all these fancy rules, we're going to work out how to differentiate tan because he was the odd one out. So how do we differentiate tan of x? Righto, so let's rewrite it like this. So we have f of x, actually let's just write it as y, because it's going to get a bit tricky in a second. So y equals tan of x. And we want to work out what dy dx is going to be. So, tan of x is the same as sine of cos, is it not? So y is sine of x divided by cos of x. So, we can see here, if I want to differentiate this, this is going to be a quotient rule, which we just proved. How fantastic. So our top function, we'll call that f of x. So f of x is equal to sine of x. And the bottom one we'll call g of x, not q of x, sorry. G of x. Righto, so now we're going to copy our quotient rule that we just proved. Copy and move them down here. So in order to work out what dy dx is going to be, we need the derivatives of f of x and g of x. So f dash of x is going to be cos of x. G dash of x is going to be minus sine of x. So I can replace this guy here and this guy here and here, and I can place this guy here, and finally but not least this guy here. So what I'm going to get is this dy dx. Actually, let's move that down just a little bit. So dy dx is going to be, alright, cos of x times by cos of x minus f of x, which is what's f of x? Sine of x. Sine of x times by minus sine of x all on g of x, which is cos of x. So cos of x all squared. This front bit here, negative times negative is positive, so what I'm going to get is cos squared of x plus sine squared of x, all on cos of x all squared. This is Pythagorean's identity, which is equal to 1, so I can replace that with 1. So I get dy dx is equal to 1 on cos of x all squared, which is the same as 1 on cos squared x, which is sec squared x. So if you differentiate tan x, you're going to get that as one ugly looking tan. Alright, so if you differentiate tan x, you're going to get sec squared x. Okay. Righto, so now that we've done that one, we can learn how to differentiate tan inverse. So if I want to differentiate tan inverse, I have no idea what that's going to get us. But it's not going to be similar to sine inverse and cos inverse. So what I have is y equals tan inverse x on a. So I don't know how to differentiate this, but I do know how to differentiate tan. I'm just going to have a sip of my coffee. Damn, this is a long video. Alrighty. I'm not doing this off my head either. I wrote this all down before I had to go at this. But yeah. So, tan both sides. So tan of y gives me x on a. Multiply both sides by a. X is equal to a tan of y. Dx dy is going to be a sec squared of y. So that means dy dx is 1 on a sec squared of y. Now, I want dy dx in terms of x, not y, so I need to replace that sec squared of y with something else. So, we're going to take a look at another Pythagorean identity. So tan squared of an angle plus 1 is equal to sec squared of that angle. So in other words, sec squared of y is equal to tan squared of y plus 1. So if I place that in there, I'll get dy dx is 1 on a times by tan squared of y plus 1. Righto. Tan of y is this. So if I square both sides, I'm going to get x squared on a squared. And then I can replace this guy here. So I'm going to get, alright, dy dx is equal to 1 on a times by x squared on a squared plus 1. Now I'm going to factor out a 1 on a squared. So this is what I'm going to get. 1 on a squared, x squared plus a squared. So if I were to multiply that all out, I'd get this expression here. So what I'm going to get is, if I take that outside, I'm going to get dy dx is equal to 1 on a times by 1 on a squared is 1 on a times by x squared plus a squared. Flip and turn that, times that by a on 1, that gets rid of that. So I get dy dx is equal to a on x squared plus a squared. So, finally, if y is tan inverse of x on a, dy dx is going to be this guy up here. So, in other words, derivative of tan inverse of x on a is equal to a on x squared plus a squared. Ta-da! And that is all the derivatives I'm going to be doing. If you want any more, go find something else. Now let's take a look at integrals. So, that is where it all pretty much concerns with derivatives. Now integrals are built from derivatives, and you'll see that. So, if I have f dash of x, and that's equal to a function, an integral undoes the derivative. So in other words, if I integrate f dash of x with respect to x, this will give me f of x again. Okay? That is the idea. So this symbol undoes derivatives, undoes the derivative operator. So d on dx. Okay? That's the idea. Now, there's something else it also does. So for example, if we differentiate a constant, we're going to get 0 because of the power rule. Differentiating 5 is the same as differentiating x to the 0. Bring that 0 down the front, and 0 minus 1, which gives us 0. So, when we have a function like this, so let's say we had y equals f of x plus a constant c, and I differentiate that, I get f dash of x, and my constant is goodbye. But if I integrate that, it undoes my derivative. So the reason why it undoes that is because what it does mechanically is it cancels the dx's here, and the integral undoes that change in y. So we get y equals the integral of f dash of x with respect to x, which gives us f of x. However, we lost our c, so we need to do a plus c to account for anything we've lost when we differentiate it. Okay? So, in other words, y equals the integral of f of x with respect to x. Now this dx here tells me what variable I'm integrating with respect to. This is going to be equal to another function, the integral function, plus some constant pretty much. Okay? Now, let's take a look at what else it can do. So for example, let's say we had just a curve. Let's go f of x. And we have x and y axis. And let's say we had a function a of x. Now a of x gives you an area up until a certain point x. So for example, if x is 5 and I put in a of 5, it gives me this entire area exactly under the curve. Okay? Now, let's say I wanted a specific region. So in other words, I wanted this region here. So let's say this was x, and I want a distance h, and this is x plus h. And I wanted this region here. Well, the exact area of this will be a of x plus h minus a of x, would it not? Now let's take a look at what we have here as well. We've got this situation where we have this funny looking shape here, but we know the heights of it. So for example, we know the height here. Because that's x, that's going to be f of x. That height there will be f of x. We know the width is going to be h, and we know the height here as well. The height there would be f of x plus h. So the exact area of this thing here is this guy here. But we can also approximate it using two different shapes. So I'll show you what I mean. So if I move that to the side, this is the kind of the shape I have at the moment. Okay? I could work out this area first here, which would be f of x plus h. That would be the height up until that point there. And the width is h. So I could work out that area there. So that area there would be f of x plus h times by h. Now I can also work out the area up until this point here, which would be a bit more, wouldn't it? So this whole area would be f of x times h. So f of x times h. Now this area is less than the exact. So we can say, alright, f of x plus h times by h is less than or equal to a of x plus h minus a of x. And we know that this red region is greater than, so we can say this is the exact region is less than or equal to f of x times by h. Yep. So, from this, we've basically named some function here. Now, at first we called it an area function, but because we've associated the operation of area now with it, this is now the exact area function like we defined it to be, because we've now made that association. Now, if we're trying to work the area under a curve, let's draw it again. So we have the area under the curve, and we want that region there. If we use rectangles with our width h like we have, we're not going to get a very accurate thing, are we? But if h gets very, very small, we can fit more rectangles, which in turn would make the area more accurate. So, as h gets smaller, the area gets accurate. So in other words, if I apply a limit to our expression above, we can work out an expression for our exact area. So, in other words, if I divide everything by h, because it's common in everything, it cancels out there, doesn't cancel out in the middle. So what I'm left with is f of x plus h is less than or equal to a of x plus h minus a of x, all on h. and is less than or equal to f of x. So, if I apply the limit now to make my widths very, very small, this is what I'm going to get. Well, for starters, if I apply the limit here, apply it to the entire expression. This first bit, as h goes to 0, this is going to turn to f of x. In the middle, I'll just rewrite the limit there. And hopefully you can see a pattern starting to appear. And here, there's no h there, so applying the limit would do nothing. Now, if something is greater than or equal to something, and less than or equal to something, it must be equal to it. So in other words, if 5 is less than or equal to x, but x is less than or equal to 5, that means x must be 5. So in this situation here, f of x must be equal to that little bit in the middle. So in other words, f of x is equal to this entire expression here. So I'm going to copy that and paste it. Ta-da. And hopefully you'll see this is the derivative of a of x. So what does this mean? It means if the derivative of a of x is f of x, that means if I integrate, so in other words I undo the derivative, I will get a of x, an area function. So if you integrate under a curve, you get a specific area. Now, what that means specifically is you can find exact areas. So in other words, if we take our idea now, so we have this idea to the side now, that gives you an area function perhaps, okay, with some c. Let's say I had f of x, and I wanted this exact area here. This area, let's say this was a and this was b, this area would be a of x, a of b minus a of x. A of b minus a of x. So in other words, the way we can account for this is we can write our bounds on an integral. So we write the lower bound down here, and the upper bound up here. So the integral of f of x, respectively, is going to be equal to a of b minus a of x, a of a, sorry. We can rewrite this like in square brackets. So we can say that's a of x and have square brackets here with the bounds. So in other words, if we integrate between a and b of f of x, it's going to give us an area function with the bounds a and b. And if we put in the big bound first and subtract the area of the little bound, we'll get the region we desire. And that is the fundamental theorem of calculus. Now, all of our derivatives we proved at the start of the video. So the derivative of our power rule, bring that power down the front, subtract the power by run. If we integrate something, integrals is the opposite of differentiation. So rather than bring that power down the front and subtracting it by 1, we're going to add 1 to the power and divide by that new power. Now we're going to account for a constant as well, if there's no bounds. If there is bounds, the reason why we don't put a plus c is because let's say we put a plus c here. We would have a plus c here and a plus c here, but there would be a minus in front of it, so the c's would cancel out. So with bounds, no plus c is required. However, without bounds, a plus c is required because of the idea of integration and differentiation. So differentiation gets rid of all those constants. So no bounds, you need a plus c. Righto, what else did we show? Alright, if the derivative of sine of x gives you cos of x, that means the integral of cos of x is going to be, with respect to x, so you can't forget the dx, is going to be sine of x plus c. The derivative of cos of x is going to be minus sine of x. So that means the integral of sine of x with respect to x must be minus cos of x. Because if I had the negative here, let's say I had the negative integral here. So integral of minus sine of x gives me cos of x. I can take out that negative 1 out of the operator. And then if I wanted to, I could divide both sides of the equation by negative 1. So in other words, divide this side by negative 1 and this side by negative 1. Gives me a negative here and no negative there. The constant remains the same because it could be any constant on the number line. So that's why the integral of sine of x is minus cos of x plus c, when we know this information here. Okay? Alrighty. If the derivative of e to the x gives you e to the x, pretty easy. The integral of e to the x gives you e to the x plus some constant you don't know about. And then finally, if the derivative of natural log gives you 1 on x, that means the integral of 1 on x dx is natural log of x plus c. Righto. So, what else do we got to account for? Oh yeah, if the derivative of sine inverse of x on a gives you 1 on the square root of a squared minus x squared, that implies the integral of 1 on the square root of a squared minus x squared dx is going to be sine inverse x on a plus c. Righto, let's go to the side again. We're running out of room a little bit. If the derivative of cos inverse of x on a gives you minus 1 on the square root of a squared minus x squared, this implies the integral of minus 1 on the square root of a squared minus x squared dx gives you cos inverse of x on a plus c. And then finally, like we just proved before, if the, I'm just going to write down here, if the derivative of tan inverse of x on a gives you a on a squared plus x squared, this implies the integral of a on x squared plus x of a squared plus x squared dx gives you tan inverse of that plus a constant. Righto. Now we're going to take a look at the product rule. The product rule can also be changed. So the product rule basically says if I have y equals f of x times g of x, that means dy dx means f dash of x times g of x plus f of x times g dash of x. So diff one, leave the other. So in other words, we have the derivative of a function u times v. So u and v are functions of x. We get u times v dash plus u dash times v. Righto, so well, let's change this now. Let's integrate everything. So if I integrate everything, I chuck integrals everywhere. This undoes everything over here. So all we get left with is u, v plus some constant. Now I can break the integral up if I wanted to into u v dash dx plus the integral of u dash v dx. So the integral is separable. Now all I'm going to do is move this guy over there. So all I'm going to get is integral of u v dash dx gives you uv minus the integral of u dash v dx. Righto. Now you probably didn't need to include a plus c here because we can account for that in that integral as well. Right, and this is what we call integration by parts. So integration via parts. Righto. Now, let's say we know that if we integrate between two bounds, we get the area under a curve. So, in other words, if I integrate between A and B, it gives me that area there under f of x. But let's say I want to work out the area between two curves. So in other words, if I have x and y, I have a curve here and a curve here. How do I work out that area there? So first of all, we gotta name these curves. So let's call this top one f of x, and let's call this bottom one g of x, and we need specific bounds you need. So a and b. If the integral gives you the area under the curve, that means the integral of a and b of g of x dx will give you that area there. Now, the integral of a and b of f of x dx will give you this entire area there. So if you subtract the two of them, so in other words, you subtract the red one from the blue, from the purple one, you will get the area in between. So in other words, this area here. So if you want to work at the area between two curves, like the situation we have right here, so any arbitrary situation where it's g of x and f of x, and you want to work out this area here, it's going to be integral between those common bounds a and b of f of x minus g of x with respect to x. That will give you the area between curves. Okay. Now let's understand what this integral is asking. An integral is actually a stretched out s. So it actually means a continuous sum. Like this symbol here. This symbol means a discrete sum. This means continuous. So when we actually break down this picture, this is what we have. We're adding up a bunch of rectangles with heights of f of x, and their widths are little changes in x because h goes to 0. So they're all dx's. So what we're actually doing, if I delete that, is we're summing height times width. That's all we're doing over a continuous thing. Okay? Now the final thing I'm going to prove is a volume of revolution. So imagine another curve, and I have f of x again. And I decide I want to rotate him around the x-axis. So in other words, I kind of get a volume here. Some volume looking thing. If I take a look at this, I'm going to get this kind of little disc here. Now let's say I need this incremental distance. So for example, all along here, that's going to be dx. Okay? Now, if it's getting rotated around the x-axis, that means this is going to be a circular path. So this bit here is going to be completely circular. So if we imagine if I put this flat down, this is what I have. I have a disc, and I have a base, and this height here is dx. And the radius is going to be the distance from here, which would be f of x. In other words, f of x is y. So this would be y. Now the volume of this would be pi times the radius squared, so y squared, times the height, which is dx. So if I want not just one little disk, but over a specific volume, so between two bounds, a and b, I just have to integrate between them. So for example, the volume over a specific distance, and I rotate it, will be pi integral of a to b of y squared dx. And it's the exact same thing for if we rotate it about the y-axis. So if I had a curve here, f of x, and I sometimes wanted to rotate it around like that. It'd be the exact same thing, except the radius would be x, and it'd be with respect to y. So those are the volumes of revolution as well. I hope you enjoyed this video where I proved nearly all of calculus. Obviously there's some bits I missed out, but majority of it is here. I hope you enjoyed this video. Like and subscribe, please.